All right, I think we can probably get started. I know first talk in the morning, everybody's not really awake, and that might be a good thing for me. Maybe not so good for you. So I'm Andy Rudoff from Intel, and in these conferences, I tend to either come representing Intel, talking about what Intel's doing, or I tend to come representing the SNIA NVM Programming Technical Work Group, or the TWG, and kind of give a report of what they're doing. So this time I thought I'd do something a little different. I'm gonna firmly plant a foot in each one of these roles and talk about the difference between what we did in the TWG, what we wrote into a specification, and then what actually got implemented out there in the wild. And that's why I said, theory and practice, right? What is the theory behind this programming model that we wrote up? But then what really happened? Because it doesn't really matter what you write into a spec if you don't own the OS, right? The people who own the OS are gonna do what they're gonna do. And so some kind of interesting differences came up, interesting enough that I thought they warranted a talk. So just to set your expectations here, I will do a very brief introduction to why we even created the TWG and the model. And if you don't know what the NVM programming model is, and you haven't seen the diagram that I've shown a million times, don't worry, by the end of the talk you will know what it is. But mostly I'm going to focus on these sub-bullets here about what does it really map to on Intel hardware, in Linux, in Windows, in some of the virtualization solutions out there. And then I will talk a little bit about where we're going in the future. Okay, so what motivated us to actually create this thing? The technical work group, the TWG, was really the idea of a couple of people sitting in a room something like 5 years ago. And if you look at these things that were emerging in the market at the time, these NVDIMMs and other types of flash cards that went into the PCI bus, and also just NVMe drives, but with people adding vendor-specific features to NVMe drives, it was all kind of going in different directions. And I was really worried, a lot of us were really worried that just an ISV would be forced to lock into one solution and then rewrite their code for another solution. And it had already happened. And I think it's probably safe for me to poke fun at it now because the company's kind of gone now. But Fusion IO had this card that had flash on it. It went into the PCI bus. They had a private interface, an API called VSL, I think it was called in the kernel, that you could call a virtual storage layer, maybe, something like that. Anyway, the point was, it was closed sourced, and it was a private API. You couldn't even really learn about it without buying the product. And if you wrote to that API, it didn't work on anybody else's. Nobody else's drive or memory or anything like that. It didn't work. And people were already getting kind of annoyed that they locked into an API. And I think that even Fusion IO started considering, well, what should we do about that? And they did start to open some things up, I think, before they got bought. And so this lock-in thing, a lot of conflicting ideas about how these APIs should work. It seemed like we should get together. And so a couple companies got together and said, okay, let's have a work group about what the programming model is. And actually, overnight, it was a whole bunch of companies. Everybody joined in. We got some very key participants from the first day, including Microsoft, which was very supportive from day one. Red Hat, you don't usually see the Linux guys in a lot of these standards bodies, and Red Hat said, yes, this makes sense to us. They joined SNIA just to join the TWG. We had Fusion IO was there, and VMware was there, and Dell and Oracle, and just a lot of these companies. HP chaired it, co-chaired it with Intel, and so it really was sort of an overnight success, and meaning that everybody agreed this was a problem that needed to be addressed. But my reasons were maybe a little bit different if I put my Intel hat on, because back then we hadn't said anything about it. But of course, and I swear this is my only marketing slide, my reason was that this product was coming, right? So this was, like I say, this is 5 years ago. Nothing had been announced. In fact, the name 3D Crosspoint, which is the media, we hadn't come up with it yet. Certainly this weird brand name Optane hadn't been come up with yet. Don't tell the marketing guys I said that was weird. But the point is, I knew that this was coming. I knew we were going to have these gigantic capacities, like, you know, 0.5 terabyte per DIMM, right? So I knew that finding a unified programming model across operating systems was a really important thing. And so I have to admit, I kind of leveraged the fact that these other NVDIMM products were out there and that they were already available in different systems, for not just Intel systems, but all sorts of systems, right? Not one OS, but lots of OSs. So I basically used the NVDIMMs that were out there to help make my case, to say, you know, we really need a unified programming model. But of course, with my Intel hat on, this was why, right? I was really trying to make sure that when this stuff became available, we would have a model ready. So what everybody should know about persistent memory, we spend a lot of time in these types of talks talking about, you know, how do you modify your program to really leverage what persistent memory can do? How do you modify your program to do these loads and stores directly? Oh my gosh, transactions are hard. How would you write that in code and things like that? And people see these talks and they're like, oh my God, I have to do that? I have to change my app? That's a lot of work. So we spend a lot of time talking about it because it's the hardest thing you could do, and we want to make sure that people understand it. But actually, there are many ways to use persistent memory without ever modifying your program or modifying your system. In fact, you might not even know that you're using it, right? Because there are many ways that it gets used in lower layers of software. It gets used by the OS. It can look like a disk drive. It just looks like the fastest SSD you've ever seen. But then no programs have changed. It can be used as another tier of memory inside the OS. It can use it as another tier of memory inside some library. And so we have a lot of examples of this. And I'll touch on it a little bit, but I just want to make sure everybody understands the reason we talk about the modifications to your programs for persistent memory is because that's the hardest thing you could do. It's the best leverage you can get to. But it needs to get a lot of airtime because it's a hard thing to do, it's a hard thing to understand. But I still think, you know, for years, the common case is people are just going to use it in one of these legacy modes because they don't want to modify their app yet, right? It's just like when we had the explosion into cores, many, many cores, right? For years, we had single-threaded programs out there. This is now, 20 years ago, right? We had single-threaded programs out there, and then when the core explosion happened and suddenly every machine was a multiprocessor. Even your phone, even your laptops had multiple processors. The programs that were single-threaded still worked. And everybody was fine with it. And they didn't have to modify their program. It still worked. But we had to teach the community, the ecosystem, about multi-threaded programming. And eventually they all said, well, if I don't want to get left behind, I need to multi-thread my program and get the better performance. And it still works single-threaded. So that's exactly the situation with persistent memory. It's going to work great if you don't do anything. You can use it as a fast SSD. You can use it as another tier of memory. You won't even know it's there. Your program will work great. Life will be good. But eventually the ISVs will start to say, wow, I'm going to get left behind if I don't really leverage what persistent memory can do. And that's why we're spending so much time talking about how to use it. So the programming model is for those applications that want to make the change. We have many major applications have already announced publicly that they've made the changes. Some very big databases, SAP and Oracle and Microsoft SQL, all those databases have made public announcements, and many of them have done public demos already that they are modified for persistent memory. We have libraries like the Persistent Memory Development Kit there that builds on top of the programming model that I'm going to talk about. But this talk isn't about PMDK. We have one coming up shortly later this morning. The two people sitting over here are going to talk about it. And so if you're interested in hearing about that, stick around. There's also kind of a very interesting aspect of persistent memory, and that's the ability for us to communicate with it on remote nodes over things like RDMA. I'm not going to cover that because it's a whole big topic itself, but the next talk right after mine by Tom Talpe is going to cover that. So again, stick around if you want to hear more about that. Okay, so let's talk about the programming model. What's the high order bit here of the programming model? It's a model, not an API. Now, this was actually really important for us to get these companies to participate. Everybody hates to be told that they have to implement some API, especially, when people come up with these generic APIs, they're the same on Windows and Linux. They abstract away all the differences between Windows and Linux. They're usually pretty ugly APIs. Nobody likes them. They have some weird, they can't use file handles or file descriptors because those are specific to the OS, so they have some weird descriptor that nobody knows what to do with, and they have some new language that they had to come up with to make up the difference between where one OS uses a slash and the other uses a backslash and stuff like that. So we knew that was just not going to fly. We said, let's define a model for programming to persistent memory, and then that each OS can have a mapping. The model maps to my OS in a certain way. We decided that we needed to define the model both for in-kernel and out-of-kernel use, so kernel and user space. And to be perfectly honest, when I first started this, and I'm not making this up, the people who were proposing how persistent memory programming should work on the Unix-like operating systems, there were varied proposals, and one of the leading ones was to use the System 5 shared memory interface, which I hate, and where you get each, memory has a little ID. There's no permission model. It's horrible. The IDs are not persistent, so how do you look them up again? There's no naming. It was just a terrible idea, right? So I just wanted to kill that idea. And then on Windows, there was a similar idea. Oh yeah, they ought to be little numbered regions, and the numbers are stored in the Windows registry, and you look them up. And it just, again, there's no permission model, or they would make up a new permission model, right? So people understand how file permissions work. They might not be perfect, but they've been around for many decades. People understand that. People understand how file names work. So the only thing I really wanted to achieve was, let's just use the file system namespace. Open up the file, memory map it, and then you have your persistent memory. That's all I wanted. And sure enough, in version 1 of the spec, I got it. So at that point, I'm like completely happy. Wow, we achieved our goal. We got all of these, by then it was about 40 companies who were members, but 10 or so were active, very active in the TWG. But after 1.0 was published, we had achieved our goal. And so the rest is just the details on top of that. I was actually quite happy with that goal. Now, our chair, who recently retired, Doug Voigt, gave a talk at the Flash Memory Summit just a month or so ago. And he showed this slide with the 4 modes that we put in that spec. And so this is kind of the summary slide we use all the time to say, well, what was the spec about? And what you can see is that we actually, it's called the NVM Programming TWG. It's not just the persistent memory programming TWG. So one type of NVM are these block devices like NVM Express drives, for example, or other types of SSDs. And so the user space model, we called it NVM.file, and the kernel model, we called it NVM.block. And this was the place, we call it innovation. This is the place where as you add features like new kinds of semantics to drives, this is where they would go in the programming model. And we meant for this to be something that would evolve over time. Now, in practice, we wrote it down once, and then everybody ignored it because everybody was interested in the persistent memory side of it. So this part of the spec hasn't changed since 1.0. And we might have fixed a spelling error or a typo, but other than that, it hasn't changed. On the persistent memory side, though, we also have a user view, which we call nvm.pm.file, and we have an in-kernel view, which we call nvm.pm.volume. And this has been the focus of our work, right? And this part has evolved and will continue to evolve. So this is kind of the TWG view, the TWG summary of the spec. But I always draw this picture. And so now, me with my Intel hat on, this is the one that I like to really drive out there as the programming model, because I think it's more to the point. And it shows, the persistent memory is down here on the bottom, and there's some set of drivers. It's different for different OSs. So I just sort of put this blob here and say generic NVDIM driver. But the point is there's some set of drivers here, and it exposes things for manageability on the left side of the diagram. It exposes things through the legacy path. That's what I was talking about before. It can just look like an SSD, and no applications need to be modified. Or, this is the exciting part, you can expose things through some sort of persistent memory-aware file system, and that means that if an application uses standard APIs, so now I'm talking about POSIX on Linux or the Win32 file APIs on Windows, You use those standard APIs to memory map it. You get this thing on the right. So this is the whole point. You get direct load store access to your persistent memory. And both Windows and Linux nicely named this direct access feature DAX, which is nice. It's nice they use the same term, but as you'll see in a minute, it doesn't quite mean the same thing between the two OSs, unfortunately. So this is the point. This is how, if you do want to modify your application, you can get this direct load store access, right? That was the whole point of the model. So now let's talk about what really happened. We wrote it in the spec. How does that map to the actual hardware? How does that map to the actual operating systems out there? So first of all, let's talk about how the Intel platform works. Intel platform is fairly popular out there in the ecosystem, and so it's worth talking about these things, even though they do tend to be mostly Intel specific, or at least the Intel IA architecture specific. So on Intel, the way that the firmware in the platform communicates the configuration of the system is important. You want to be able to communicate up what's installed in the system. You don't want the operating system to say, oh, there's DRAM and there's persistent memory and it's just one big pool and I can just use it however I want, right? You don't want the operating system to just sort of stumble into the persistent memory and start using it like regular memory. You want it to be special so that people can get to it in a special way. So we added a table to ACPI starting at version 6.0. You can read it. It's on acpi.org. You can read it. It's a very easy URL, so I didn't even bother putting it on the slide. And it's called the NVDIMM firmware interface table. So the NFIT is what tells you what persistent memory is plugged into the system. And in particular, when I say you, it's what tells the OS what's plugged into the system. Okay, and I also put smart there. You know how disks have this smart information you can look at that tells you their health? Well, we came up with something similar for persistent memory. So that's also in the spec, and it's how you ask it, how's your health? How worn out are you? Things like that. Historically, there's been this thing called the E820 table, and of course, we had to define what does it mean for persistent memory? What goes in the E820 table to make sure the kernel knows that it's different? There's another table that has just more recently been defined called the HMAT, that stands for the Heterogeneous Memory Attributes Table. And the HMAT is actually a very useful table, but it's not even implemented yet. It's relatively new. You're going to see it in platforms, well, pretty soon. And it's what tells you a lot more detail, like the relative performance of all the different types of memory in the system. And this is going to turn out to be really important. We didn't think of it. In the days of INFIT, we didn't think of this until later. But now we realized that you need a way to learn a lot of the other attributes of the memory that's in the system. And then finally, UEFI, the booting standard, which is, you can see it at uefi.org. You want to be able to boot from persistent memory. And so we came up with a layout for making persistent memory look like an SSD, where blocks are written atomically and so on. And that's all defined in the UEFI standard. So we also found that if an operating system had to communicate directly with all these different brands of NVDIMMs, then the driver couldn't be generic. Remember, I said it was a generic driver on this previous slide here. Well, I at least want people to be able to write a generic driver. So I can't have the driver knowing all these gory details of every NVDIMM. How do I talk to mailboxes and submit commands and so on? So the way that we handled that was we started defining these device-specific methods, which are calls, essentially calls into the BIOS. These are not for fast operations, right? These are for operations that aren't very frequent, like manageability operations. So these aren't all standardized because some of them are device-specific, vendor-specific. But you can make a generic driver, at least on Linux, that's how it works. The driver has no idea what's inside most of these DSMs. And a management piece of software that might come, might buy one of these Optane DIMMs, and then you might take the Intel tool to see how its health is or to manage it. And the Intel tool can just use a pass-through interface to send down these DSMs. So it was a way of sort of isolating knowledge out of the kernel. And then finally on Intel, well, there are CPU caches, right? So if I do the store, I just got through bragging that it was really cool. An application can store directly to the DIMM, but there are caches. So if I do a store, usually it goes into the CPU cache. So how do I get that store out of the CPU cache and down onto the DIMM? Well, there's a CPU cache flush instruction. There used to be a second level flush that you had to do called pcommit, but we decided before that ever shipped that it was a bad idea. And when I say we decided, I mean we, with a lot of feedback from our customers.
That's a nice word.
Yes, feedback, strongly worded feedback, saying you're making this too complex, you're making this too hard. And you'll see on the next slide what we did instead. But there are these other mechanisms for managing caches and managing the path of a store down to the DIMM that are fairly Intel specific, but what we're finding is that other architectures, ARM and Power and so on, have similar mechanisms. So they can be nicely abstracted away by a library, and our libpmem in the PMDK does do that. But again, let's talk about how it works on Intel, because I'm kind of mapping this model to a piece of hardware. So this is how the Intel hardware works. So up on the upper left is a store instruction. It's called move on Intel. And you can see, like I said, it goes through some caches, some CPU caches here. And eventually it makes its way through the memory controller on the system. And there might be a little queue in the memory controller called the write pending queue, where things sort of queue up to go across the DDR bus. And then it heads out and it ends up on the DIMM. So it takes that red path. And so what you really want to know is, well, if I'm writing a piece of software and I've done one of these stores and I lose power, how do I know the store is persistent? So what you really want is this big red box. You want this to be the persistent domain. In other words, when you do a store and the store is complete right here, you want to say, oh, good, it's persistent. You might want that, but you're not going to get it. And you're not going to get it because these caches are huge. Right? And so in order to give you that big red box, we'd have to either make the caches right through, in which case performance would kind of start to suck, or we would have to flush these caches automatically on a power failure. But they're megabytes, right? So you'd have to take the car battery and hook it up to the system to have that much stored energy. And we didn't feel it was a viable solution to require every system out there to have the car battery. However, what about the smaller red box? What about saying, okay, fine, it's on software, it's on the application, it's their responsibility to flush it down out of the cache, but we'll create this smaller persistent domain. So if the store hasn't made it all the way to DIMM, if it's sitting here in the memory controller, we will require the platform to have that much stored energy. And that's exactly what we did. And those platforms have a feature called ADR, which unhelpfully stands for asynchronous DRAM refresh. But what it really means is a system that has ADR has enough stored energy in the capacitors of the power supply to complete this trip. If a store is accepted by the memory subsystem and you lose power, it goes all the way out to the DIMM automatically. And we require it. All NVDIMMs require it. All the NVDIMMs on the market today require ADR. And so it's not just our DIMM. And so that means you can count on not worrying about this part of it. But if you're an application, you are worried about this part of it. Now, I think in the future, people are going to build platforms with the car battery in it, right? Because it's cool. It's actually very handy. You get a nice performance boost. You do these stores, and the stores go into the cache here. You don't have to worry about the flushes. It all happens later. And a lot of the stuff just evicts naturally through the hours and hours of use. So we're definitely seeing movement towards this direction. So to anticipate that, we defined the ACPI property that tells you if this is the persistent domain. It's there. It's in ACPI 6.0 already. And we think applications should be looking at that property and deciding whether to do the flushing or not. Okay, now if you decide to do the flushing, there are several flush instructions. I won't go into them in detail. Last year essentially in this time slot, I gave a whole talk on the different types of flushes. The slides are still up from last year's SDC, so if you're interested, you can go see. But there are several instructions for flushing, and there are also mechanisms for draining this queue if you want to forcefully make sure that it's drained. We call that a deep flush. Even though this is part of the persistent domain, if for some reason you want to make sure that something is flushed all the way down because you're trying to make sure that those stores are held to a higher standard, they have a lower failure domain, you can actually drain this intentionally, and that's called deep flush in the SNIA spec. What I don't show on this slide are things like what happens if you read an uncorrectable. You know, what's the mechanism? And we call it the machine check architecture on Intel. And it's what happens when you read this thing called poison, and the poison gets passed around. As soon as somebody tries to consume the poison, they get a machine check, and it's really ugly. And sometimes the machine crashes, and sometimes you can keep the machine running. It's a whole nother set of slides. And kind of the reason I don't show it on this slide is it's pretty complex, and it's not part of our spec. It's not part of our programming model. Maybe it should be. In addition, there's how do you detect if ADR doesn't work? What happens if your power supply doesn't do what it's designed to do, and ADR fails? You don't want silent data corruption. You didn't get everything down. So how do you detect that? Again, we have an answer to it. It's a whole other set of slides, but it's not in the programming model. And again,
It will be in the new one.
but in the,
Fail.
yes, in the new one, that's true. We wrote it in. We at least described the problem. Thank you, Tom. So what am I saying an application has to do? Is an application's responsibility to do this logic. Now, this logic can happen once at startup, so it's not that bad. It's not a heavy lift for an application. And just to save you all from suspense, of course, PMDK does all this for you, right? So if you just decide to use our libraries, they handle all this. But basically, when a program starts up, it says, well, okay, do I have that DAX, that direct access? If not, I should just be using the standard APIs. Don't try and do anything else. Don't try and do anything special. They will work. They'll work as expected. Open, close, read, write, mmap, msync, and the equivalent on Windows, flush file buffers and map view of file, things like that. It'll all just work. But if the OS tells me, yes, you do have the persistent memory mapped using DAX, then you want to ask about that property I just mentioned. You look at ACPI and you say, are the CPU caches considered persistent? If they are, that means your stores are persistent as soon as they're globally visible. And that's awesome. It's easy. All you got to do is do a store as soon as it's globally visible, which is a semantic of the memory model on every platform. You can assume that it's persistent. More likely, in the near term, for platforms that have CPU caching and it's not persistent, then you're on this path over here, and you have to look to see, do we have this fancy new instruction called cache line writeback, CLWB? If you do, you can use that. If not, do you have this not quite as fancy, but still pretty useful instruction called CLFlushOpt? If you do, you can use it. If not, there has been an old instruction called CLFlush. It's been around forever. It's not quite as optimized as these other, but it's been around for years. So this little tree is what an application does on startup. And the way we do it in our library is we figure all this out when you map a file, and we just keep little function pointers to the functions that do the correct type of flushing. So there are no more decisions after that. It's just that every time you try to flush after that, it calls through a function pointer. And so the decision's been made once. Sure.
Okay, so that far right path, does that mean once everyone does that, we don't have to do transactions?
What a great question. The far right path, right here, if stores are persistent as soon as they're visible, do we even need those libraries anymore? Can we just throw that away? That we don't need transactions anymore? So the flushing isn't actually the hard part in PMDK. It's the transactions. And you need them whether you flush or not, because anytime you want to change a data structure that's bigger than 8 bytes, you could have a power failure in between the store instructions, and you have a half-done change, right? So those changes, anything you want to change, let's say it's just 16 bytes or something, right? Anything you want to change, it's not atomic with respect to power failure. Now, Intel has instructions that can change 16 bytes atomically, but that's atomically with respect to visibility to other threads. It's not atomic with respect to power failure. So you still need some logic that says, okay, I'm going to write a little record that tells me I'm about to change these 16 bytes, and now I'm going to go do it, and if I get interrupted, that record that I wrote gives me enough information to either roll it back or roll it forward. So you still need it for transactions. Just like you still need transactions on storage for database things. So it's exactly the same problem. Anytime you want to change something significant, you have to build the transactions with write-ahead logging or undo logging, some kind of logging usually. That's a great question.
The NVMP document talks about the transaction model in much more detail.
So yeah, in the programming spec,
Application consistency.
right, we cover, in fact, we really try to make people aware of the problem. We don't particularly talk about the solutions in detail. Okay, so now I kind of gave you this is how it works on the Intel hardware. So how did our programming model end up in Linux? Now, this is the biggest section of my talk because we dive into most of the interesting details. And that's not to say that Windows didn't do as much work and didn't do as much interesting stuff, but actually Windows very closely followed the model. We spec'd it, they followed it. With Linux, that didn't quite happen. And there's an important reason for that. An important reason is that the Windows guys were in the room when we made the spec. It wasn't Tom, actually. It was one of your predecessors at the time. And those are the same people who go back to Microsoft and report back and say, oh, this is what needs to happen. With Linux, we had a member of the Linux community in the room, but there isn't like one person, unless it was like Linus himself, there isn't like one person who's going to come in and decide how it works right then and there. The best you can achieve on Linux is for the guy in the room to say, oh, okay, I see what you're going for here, and then go and sell it back to the Linux community and say, this is what we want, this is what we want. But of course, what really happens in the Linux community is the Linux community says, no, that's not what you want this, right? And we're like, well, we do? What do you mean? And it is the process. And you know, it's a little frustrating if you're not used to it, but actually, it's also the beauty of the Linux community. It's the value, because you get forced to think of these things you never dreamed of, and you get forced to really defend yourself and come up with things. And Tom's laughing because he's like, yeah, sure, the value. But it is how it works, right? And actually, it was pretty eye-opening for me. I hadn't dealt with it at that level before. So Linux had this thing called execute in place. It was some old code. It was added a long time ago to basically execute a file system that was on a ROM or something like that. It was in ext2, and the code was horribly broken in all the other file systems because it just hadn't been used in a while. So Matthew Wilcox was working at Intel at the time, took that code and kind of ripped it out and replaced it with this DAX mechanism, and then did his thing. He put it out there, and the Linux community ripped it apart and fixed it and rewrote it a few times and everything. And so now it's actually quite mature, or I'd say at least more mature than XIP was. And a couple of file systems, ext4 and XFS, added support for it so that you can mount both of them with this DAX option on, and they provide the direct access that I showed you on that previous diagram. So that's been upstream actually for quite some time, years at this point for some of it, and so and that follows the programming model pretty closely, but with a few surprises. A few of the surprises are, well, so I have to admit, again, I was going for file names and the permission model. So in my mind, it was just some pseudo file system. Let's just make a little pseudo file system that exposes persistent memory. All I need is a name and some permissions. I don't need the rest of what a file system does. And it should never have to do all the other stuff file systems do. It should never even talk to a block driver or anything like that. That was my idea. And again, the Linux guys kind of told me, no, that's not your idea. Your idea is that we take one of the existing file systems and add DAX to it. And so the Intel labs had actually prototyped the pseudo file system I was looking for called PMFS and published a paper on it. And we were going to use it as the beginnings of our work, but as soon as we tried to get it to pass a lot of the standard tests that the Linux file systems go through, we realized how far away it really was from being production quality. And we realized the Linux community is right. We should just be taking one of these well-worn file systems and adding DAX to it, and that's what we did. So PMFS died on the vine, basically. And that's okay, right? That's kind of the right thing ended up happening. And as you'll see in a few slides, I think it's worth mentioning, Microsoft came to the exact same conclusion, right? Pseudo file systems aren't that common on Windows anyway, but they took their well-worn file system and added the feature to it, which I think was the right thing to do. There was another interesting thing. So we call the ability to flush in the SNIA spec, the ability to flush something to persistence from user space, we call that optimized flush. You can either use your old friend msync, it's been there forever, it'll work, or you can do an optimized flush where you just use the instructions. And my intention was that when you have a DAX file, it's safe for optimized flush. That the file system, the definition of DAX is that, okay, the persistent memory is in the control of the app, it's yours. I'm not going to mess with it. File system is out of the picture. And the Linux community said, no, that's not your definition of DAX. Your definition of DAX is the direct access, but you still have to follow POSIX. And so this was a really interesting argument in the Linux community. Basically, POSIX says that something doesn't have to be persistent until something like msync or fsync returns, right? Nowhere in POSIX is there a mechanism for you to flush without calling into the kernel. So basically, the file system maintainers were saying, we need the control point. We need you to be able to call us for msync or fsync in case we want to move stuff around. And you look at the code and you think, well, they don't want to move stuff around. It's perfectly safe. And this is a really important point. This is the most important point of the talk, right? And this comes up a lot. I can go look at the code. Linux is open source. I can look at the code. I can see how it works. That doesn't matter. What matters is what people are committed to making work, right? What matters is what's a specified documented behavior. So the fact that I could make it safe to do a user space flush for both XFS and ext4 didn't matter. It didn't matter that it happened to currently be safe, because what the maintainers were telling me was they couldn't guarantee it would always be safe, right? We might have some weird silent data corruption at some point in the future if they change how those file systems work. Didn't matter that it didn't work that way now. The argument was over what's the documented guaranteed behavior, right? That's a pretty important point. And so at the time we had this argument, we changed PMDK. The day after that argument happened, we changed PMDK so that it said, oh, it's not safe, we're calling msync for everything. And PMDK, one of our benchmarks that did an in-memory, in-persistent memory key value store, got slower by 700%. By that trip in the kernel and the serialization of taking locks during that trip, and the fact that it has to take some pretty long code paths, cost us 700%. But we put an environment variable there that you could set, that we warned people, don't use this in production, don't use this in production. But if you just want to benchmark what you think we can achieve once we finally solve this problem, you could set this environment variable and you got that 700% back. And so, of course, that's what people did. For benchmarking, they used the environment variable, and then every day they sent me emails saying, did you guys solve this yet? Did you solve it? Did you solve it? So Dan Williams, who is our Linux guru inside of Intel, spent the better part of a year negotiating on what solutions are acceptable to the Linux community. And he did a fantastic job. And the result is this flag called map_sync. If you call mmap with map_sync, you get what I had meant by DAX way back when I first made it up. Basically, you get a promise from the file system that says, oh, all right, fine. You want to take responsibility for things like flushing. I won't move anything around unless it's done synchronously. That's why it's called map_sync, unless it's done synchronously during a fault or something like that. So now, libraries like PMDK, they try and map the file with map_sync. If they're successful, they know they can use the flushing instructions in user space. If map_sync comes back and doesn't work, they try a normal mmap. And if that works, they know they have to call msync. So we can make the library safe in both cases. This gives the file system the opportunity to say no. It can actually answer no to map_sync, right? So it's a negotiation. So this was a surprise, and lo and behold, our model that we wrote in the twig doesn't cover this at all. In fact, this is a violation of our model, right? We basically say our model is that the standard API for file mapping gives you access to this. So we are missing this little handshake, and that's something that we need to fix in our spec. Because we just didn't dream of it. We didn't think of it at the time. The second thing that kind of surprised us is that we had this idea. Again, it was like a file system is for exposing persistent memory. But one of the file system maintainers said, nah, some of the files could be exposed that way and some not. So he says that the DAX thing ought to be a property that's per file, not per mount point. Cool. We didn't think of it. And again, it's not clear whether we should be calling that out or not, or whether it's just kind of a detail of Linux. There were a lot of things about doing RDMA that we didn't think of in the first spec, and a lot of that is now being discussed at length, and you're going to hear a lot about that in Tom's talk after mine. And then finally, there's this thing called device stacks. So what is device stacks? Device stacks is getting access to persistent memory without using the file system at all. Remember, I told you our model is to use this persistent memory-aware file system. Device stacks has nothing to do with our model, and I mean that very literally. Device stacks was a workaround. It's a workaround for a lot of those problems we had before. Because we had customers who needed to get things working in a way they could depend on. They couldn't wait for the map sync argument to finish. They needed RDMA to work. These long-lived registrations in RDMA needed to work. And they couldn't wait for that. So Linux guys made up this thing called device stacks that just doesn't follow our model. It doesn't follow our model at all. Here are a few surprising behaviors of device stacks. If you open up the device and you mmap it, you get direct access to the persistent memory. Cool. The read system call doesn't work. The write system call doesn't work. msync doesn't work. These are like the basics, the axioms of Unix, right? You open a file and you do read and write on it, they don't work. So device stacks ain't for everybody. It's pretty much the only thing that will work is mmap and flushing from user space. Stat doesn't even tell you the size of the file, right? I mean, it's really not easy to use. But there are lots of ways of figuring this stuff out and working around it, and PMDK hides it all from you. So if you do use the PMDK library, you can use file system stacks, you can use device stacks, API's the same. We abstract all this stuff away. But as you can tell, I'm not really very fond of device stacks. I hope it goes away. And it will go away, I think, eventually. As soon as we finish, there's a work going on right now to help with RDMA memory registrations. Right now, the long-lived memory registrations required for RDMA, they only work on device stacks because we haven't got a solution yet for file system stacks. We're getting there. And there are a few other annoyances, like there's no way to tell a file system not to zero pages and things before you use them for security. It's a good reason. On device stacks, they don't care about security, so you can skip that. So there's device stacks. Like I say, it was one of the surprises. There's nothing about this anywhere in the SNIA spec, and I don't think there ever will be, because it's this kind of weird direction off to the side. Deep flush, as I was mentioning before, that's the ability to flush something to its smallest possible failure domain. This is implemented in the driver, in the Linux driver. It's exposed via a special file in sysfs for device stacks because msync doesn't work. But for file systems, msync and fsync, they just invoke it. They figure if you're going to take that 700% trip down into the kernel, you might as well do the deep flush, because at that point it's in the noise as far as performance goes. As far as detecting when it doesn't work, that's all been left to user space. And so that's still kind of on the programmer. Uncorrectable error handling is a pretty interesting side of this, and this is something that we don't cover in the spec at all, very, very well anyway. It's tracked by the OS. There's a special API in the kernel called machine check safe, MC safe version of memcopy. File systems could use it to detect if they got an uncorrectable on their persistent memory, but none of them do yet. But the Nova file system, which is not upstream, uses it extensively and automatically fails over to replica copies of its metadata. It's actually very good work. I hope that we see that go upstream. But if an app reads an uncorrectable from persistent memory, just like memory, it's going to get a SIG bus. Unlike memory, after it crashes or after the system crashes, either one, and comes back, it's still poison, right? It's persistent poison. That's much different from poison in DRAM. So you have to go through some special steps to clear it. And on Linux, the way you do that is you punch a hole in the file, and then you write the new data. OK. I'm going to skip ahead to keep things moving and just cover Windows. So for Windows, they did everything, like I said, that we wanted in the programming model. You can use NTFS as their PMM-aware file system. It's safe to use user space flushing. You don't have to do any special flags or anything like that. There is no equivalent of device stacks. Thank you very much. There's no exposure of deep flush at all. In fact, right now in the Windows kernel, there's no implementation of deep flush. It may come later. And all the stuff that I mentioned for uncorrectables is also still planned but not implemented. So,
Internally, the kernel has a deep flush, but
Tom says internally deep flush is used.
it's used deep in the kernel for management.
All right. Okay, thank you. So, you know, I had like 6 slides on Linux, but really this is my only slide on Windows because it really follows what we wrote quite well. They mesh very well. So most of the changes I'm looking at in updating our spec is really to reflect what happened in the Linux community. Similarly with virtualization, we have several virtualization products out there, VMware, Hyper-V, KVM. They've all announced publicly support for persistent memory, and it's actually awesome because what it is it's the exact same programming model in a guest as you get on the bare metal. Programs don't even know they're running in a guest. It's the same API, even the drivers work. It's awesome. So really, there's no need for applications to do anything special when they're in a guest, and it's just great work. I'm actually so happy with the way that turned out. There are a few things that are hard that cause VM exits and so on, but again, the applications don't have to know about that, just the VMMs. So where could we have done better? Well, the spec has some of these inconsistencies, like I'm saying. You know, I think that we could just go through and I'm kind of hesitating to go in and just modify the spec to follow like what the Linux guys did. Is that even useful? But I also don't want the spec to be wrong, right? So I think we'll go in and fix some of the more glaring differences. And then in the future, we're going to continue to evolve it, but we'll probably add a section on current practices that kind of explains all the stuff that I explained in this talk. Well, here's how it actually works in practice. I think that would make the spec more useful for someone trying to read and understand the model. More work in the future is coming, and Tom's going to talk about that for remote persistent memory. Definitely we could do more around RAS and transactions, and I think there's a lot more education we could do to help people understand persistent memory. So I've talked through most of the question period. We have like a few minutes, so why don't I pause now and see what questions we have. Yeah, go ahead.
Virtualization, do you have with Docker containers?
Yeah, so the question is, what about containers like Docker? We've found that Docker, it just works for some definition of just works. You know, it inherits its file system namespace from the outer system. So if you have some persistent memory mounted, that you can work with it. What it needs is support in the management infrastructure, and that's work that is ongoing right now. So it's more of a management problem than it is anything to do with the model. Okay, I think I used up all my time. Thanks very much.